morning. I'll try to present you some main points, goals and results of my PhD thesis, which deals with some specific trajectories in Martian atmosphere in order to achieve a safe landing on some specific regions on Mars without any improvement of current technologies, so just with using only current technologies. So, okay. So there are some three main goals to in order to achieve these results. So first one was to develop an algorithm for the determination of the trajectory, ballistic trajectory through planetary atmosphere. The second one was to analyze the possibilities for landing on some specific regions in Martian southern hemisphere. And the third one was to determine optimal parameters in order to achieve these landings. This mainly means season, local true solar time, and velocity, and the angle under which we want or need to enter the atmosphere of Mars. So, what was the motivation for this research? Here you can see one topographic globe of Mars, and on the first side you can see that Mars is blue in the north and it is red in the south. It's because almost whole northern hemisphere of Mars is covered with lowlands, while almost whole southern hemisphere of Mars is covered with highlands. So there is some kind of trend of slope in Martian topography from North Pole to South Pole, with a difference in the elevation of some 6 kilometers between North Pole and South Pole. Some average difference between two hemispheres is about 2.5 to 3 kilometers. So why is this important? Because here you can see these blue spheres. They present the places where previous successful landings on Mars were achieved. So here you can see that all of these landings were achieved in the lower regions of Mars, in the northern hemisphere and in the equatorial region. So why is that? It's because when the vehicle enters the atmosphere of Mars from the interplanetary trajectory, it has huge amount of kinetic energy, which has to be dissipated, of course, by the atmospheric drag. So because Martian atmosphere is very thin, it's something like 100 times less dense than the Earth's atmosphere, it is very hard to slow down the vehicle from the interplanetary trajectory to achieve a safe landing. Because scientists and engineers always look for lower regions where they have more atmosphere in order to have more time to slow the vehicle down. And that is the reason why all of 7 previously successful landings were achieved in the lower regions. Now you can ask, okay, let's go to the north. Why should we go to the south? Well, there is scientific interest to go to the southern hemispheres. Here you can see the positions of 210 open craters on Mars, which are suspected to be the home of liquid water in the past, some few billion years ago. So there is really a huge scientific interest to explore whole Martian surface. This is the picture of Garni crater 2 years ago. Here you can see these dark slopes, which are thought to be a result of some flows of brine water on today's Martian surface. So there is really a huge scientific interest for exploration of whole Martian surface. So now, whoops, yeah. So maybe now you could get the impression that Mars is thin in the north and it is fat in the south, so that it has some like pear-like shape. But actually, that's not the truth. The point is that internal structure of Mars is like that the center of mass is displaced from geometrical center for just some 3 kilometers, and it's a huge question why is this. But because of that displacement, we have a thinner crust in the northern hemisphere, and because of that we have stronger gravity field in the northern hemisphere, and because of that we have that difference in elevation, because we measure that from the center of mass, not from a geometrical center. Here's also one more map which explains why it is necessary to explore whole Martian surface. Here you can see that in the southern hemisphere there are almost all regions from Noachian period. It's the oldest regions on Mars are in the southern hemisphere, while in the northern hemisphere are younger regions covered with recent volcanic activity. So it is one more reason why we should go to the southern hemisphere and why we have interest to explore whole Martian surface. Okay, so in order to find out how to land on those high regions, we developed one trajectory algorithm which includes one dynamical model which looks something like this, and in that dynamical model we input gravity field model, atmospheric model, and aerodynamic model in order to construct the algorithm for determination of atmospheric trajectory. First we analyze the influence of gravitational anomalies. This is just one example of flight above Olympus Mons, the largest volcano on Mars, and one of the largest geological structures on Mars. And here you can see that there is no a significant influence of these anomalies, because there is only actually this was too much for this computer. Okay, let's see some other things. The point is, very important thing is that Martian atmosphere is very dynamic. So it's not like Earth's atmosphere. It is also dynamic, but it's much more dynamic than the Earth's atmosphere. And this is the reason, because perihelion of Martian orbit is very close to the summer solstice point. So when in the southern hemisphere starts summer, then Mars is also very close to the sun because of eccentricity of Martian orbit, which is much larger than the Earth's. There is asymmetry in the insolation of the southern hemisphere here in the summer, and this is the summer in the northern hemisphere. So there is obvious large difference in the insolation, and because of that difference, there is Martian atmosphere is very dynamic. We all know that the snow falls on Mars like on the Earth, but on Mars actually, on the Earth, snow falls from the clouds, and on Mars, atmosphere itself freezes and falls down to the surface. So in the part of the year when Mars is close to aphelion, it is something like a 20% difference in total mass of the atmosphere of Mars, because part of the atmosphere freezes down and falls to the surface of Mars. Here you can see that this part of this diagram, which shows the ranges of surface and surface temperature and surface pressure of Mars, crosses this line on the diagram for CO2. So it passes from solid to gas state, and vice versa. And that is the reason of why the Martian atmosphere is so dynamic. So there is a huge difference in the density of the atmosphere. So you can see that in northern atmosphere, the density of the atmosphere changes in some regions 7 or 8 times during the year. It is something like that cannot occur on Earth, of course. And in the southern hemisphere, it is significantly higher. So in the polar regions, there can be 50 times higher higher densities during the summer than during the winter. So there is also a diurnal cycle. So you can see that also on the diurnal scale, there is a 25 or 30% change in the density of the atmosphere on some specific locations on Mars. So because the density of the atmosphere, it's intuitively obvious that it is a very important parameter when the vehicle enters the atmosphere because of the drag. So that is the most important parameter. And this is something that engineers and scientists from JPL call 6 minutes of terror. That is the critical phase of any Martian mission for landing on Mars. And it is a paradox that the whole point here that we want this time to be long enough in order to perform all these operations. So actually they want to be terrorized more in order to achieve all these events, in order to achieve a safe landing. So the main point here is to have enough time in the atmosphere, so that's the reason why they choose lower regions. So now that's question. The main point of my PhD was to find where, when, and how to enter the atmosphere in order to achieve safe landing on locations of interest in the southern highlands, so in the high regions. So we developed some algorithm which looks like this, and that algorithm, this is illustration of that. So it is some iterative procedure which starts from the desired landing site and integrate the trajectory backwards to the point of where we enter the atmosphere, and do it again and again in order to converge to the desired trajectory, and that convergence is very fast. Here you can see that only in three steps the trajectory converged to the desired one. This is this should go much faster, but okay, this is the desired location of landing, and you can see that first trajectory will miss that landing. So okay, it's too much again. Okay, but the second trajectory was already much closer, and the third trajectory was less than 50 meters from the desired location of the landing. So it's very fast and accurate. And here is the point, the other point, which deals with possibility to land on the high regions. So in order to land, as I said, we need enough time for that. So this red portion of this curve means that this is the height of parachute deployment. So we want to deploy the parachute on as much on higher altitude, as high as possible. So here you can see that the difference of the parachute deployment height during the year, this is Martian year, can go, the difference is something like few kilometers, which is the difference between northern and southern hemisphere. And here you can see the reachable locations depending on the time of year when we enter the atmosphere. In the southern hemisphere, this gray regions are reachable, and you can see that here during the winter solstice, actually that's the moment when the summer starts in the southern hemisphere. This gray region is much larger than here. So here you can see that there are currently some specific sites which are of very large scientific interest, which are in these gray regions. So that's a good thing. And also here is actually the difference of the achievable landing site elevation during the years. Here you can see that the difference go up to 4 kilometers, which is very much, as I said in one of the first slides, the difference between North and South Pole is about 6 kilometers. So this is almost 4.5 kilometers difference in the achievable elevation during the year. There is also a difference during the day. So during the day we can expect that to be almost 1 kilometer. So depending on the time of day when we choose to enter the atmosphere and to land, we can achieve different landing site elevations with difference of more than 1 kilometer, which is very significant. And here is the optimal time of entering the atmosphere, and you can see that one good thing that here is the local true solar time, so we should enter the atmosphere during the day, and that's good because technologies also require that a landing should be during the day because of some technological aspects of the process. So there is one more interesting thing, that if we want to land with some specific landing time, we found that there is a nice and simple relation between initial parameters, actually velocity and the angle of velocity vector, which is quadratic. So we can simply choose when we choose one of the parameters, we can calculate the other one by simple solving the quadratic equation. So it is very nice and elegant. So the summary would be that due to seasonal variations of atmospheric parameters, we can, let's say, relatively easy achieve landing sites with elevation of 2.5 kilometers than the current landing site that were achieved. So by optimization of initial parameters, it is possible to reach those regions. And these initial parameters have quadratic relation on the descent isochrones, which enables simple optimization of procedure. Optimal season for landing on the southern hemisphere is from late spring to early autumn. There is one big disadvantage for this, because that region on the southern hemisphere, that season on the southern hemisphere is also known for large dust storms. So that is one more thing that should be considered. And the last thing, optimal time for the landing is during the day, lights hour, which is very good. And yeah, those 3 points, red points that I mentioned before, that are in the regions of, I don't know if you can see this, but Sirenum, Simiria, and the Noakis Highlands, where there is very large possibility that even today we can find liquid water in some parts of Martian year. So that is very important. Okay, thank you for that.
Postaviš samo ovaj red uključen, vidjet će se.
Any question?
Yes. Well, this is very interesting, really, and I was at the faculty when you were talking about this first time after your PhD, and I was really impressed by all the work. I know just a little about all these spacecrafts, and I know that usually engineers and astronomers are disagreeing because engineers always want to send spacecrafts on most boring places everywhere, not just on Mars, but they are always trying to find something that is not interesting for scientists. And scientists are always arguing for more interesting things. So what you presented looks like a really nice solution for some of these things, and I'm wondering how much of your work is recognized by some, let's say, these bigger agencies that plan something like this, and how long are you in this area?
Well, a few years, so you can imagine the position of Serbian space science in the global context.
That's true, but I guess that some kind of collaborations...
Yeah, we try to establish some kind of collaboration in that sense, mainly with colleagues from the Czech Republic for now, but I hope it's a process.
You know also that Horizon 2020 is always searching for things like this, and maybe you should...
I have that in mind.
Yeah.
But I also wanted to say one interesting thing, that one of the main engineers on Curiosity lander said that because when spacecraft enters the atmosphere, it suffers pretty much damage of the heat shield. So after that, it rejects that heat shield and land. And then engineers suggested, let's go to that heat shield and to take photos and to see what kind of damage it suffered. And then the scientists said, okay, you want us to go to Mars and then to explore the thing that we brought from the Earth. So that was very crazy. So that is you're right. It is there are very large difference in the interest of scientists and engineers, and there is that trade-off between those groups, which leads to successful missions in both aspects.
Okay, just one small comment. Sorry, I really wish you a lot of luck in this field, because I think this is something really impressive, and I'm really happy to see that people from Serbia are doing stuff like this. And the second question I had is what software you used for plotting these 3D wireframe plots?
Which doesn't want, which this computer doesn't want. Yes.
Something.
It was MATLAB.
Okay.
After processed is some other mainly MATLAB.
So, are you aware? Are there any plans for a mission to Mars which would land in the southern hemisphere? NASA or ESA?
Well, for now, no. They are very. Let's say they have a long-term strategy. So they are climbing, but not so. So drastically. So they are land mainly in some a little bit higher than before. But for now, I don't know that there is some, and I don't expect it in some near future.
So one light question, because I'm really interested. Does the motion of different layers of atmosphere have significant effect on the landing trajectory? And if it does, how do you take it into account? Do you have something like functions of angular momentum, chi1, chi2, chi3, like in the case of the Earth? Or do you need some meteorological data from Mars, or so? Well, just technically?
Yes, generally actually the wind has very significant influence, but not in this sense of achieving the higher or lower regions, but in the sense of hitting, of precision of the landing site location. So in this sense, I don't think that there is some influence, significant influence on the landing site elevation. I don't expect that. It should be of help, of course, if we would have a contra-rotation of some of the layers, which would give us a larger velocity and larger drag. But I think that there is not such significant layers movement that we should. It's only a few minutes of flight, so. Let's see.
So, any question? So I have a question. You analyzed the landing to Mars, but what the inverse problem to put back in orbit? Does it symmetrical or not?
Well, it's not symmetrical. In that sense, it's better to be on higher elevation when you want to lift off. Because you will miss the densest part of the atmosphere. So in that sense, it's for some kind of sample return mission or something like that, this would be a positive aspect. So it's easier to lift off from high elevations just because of the atmosphere drag resistance.
I would say also because of the gravity, because the center of gravity is shifted toward lowlands.
Yes, but it is much smaller because in the preliminary determination of trajectory, engineers and scientists neglect gravity at all. So it's the most important, some 1,000 times more important influences atmosphere than the gravity. But so because of that, I mentioned the atmosphere. So we will miss the densest part of the atmosphere. So it's the best place on Mars where we should be lift off is, I suppose, Olympus Mons. If you want to lift off. Yeah.
Yes, but it's very hard to.
Oh yes, yes.
Okay, any question? Okay, thank you.